Hello, everyone. Welcome back. Today we're going to be covering for the Rowan University students our last chapter of the course, Chapter 10 on hypothesis tests. Plan is to cover this topic twice this week and once next week. So we're going to have 3 videos for this chapter on hypothesis tests. What we're going to do today is just do an introduction to hypothesis tests and show you the symbols involved with it and the logic behind it and all of that. And then on Wednesday of this week, I'll be reviewing the hypothesis tests for testing population proportions. And then next Monday will be a hypothesis test for testing population means. All right, so that's our schedule. And so what we're going to do today is I'll get you on my screen. Okay, and we'll go right to the PowerPoint, chapter 10. Now notice here it says hypothesis testing using a single sample. In the second semester of statistics, there would be the possibility of looking at more than one sample and making comparisons, or more than one group of people and making comparisons for a population parameter. But we're not going to be doing that in this course. We'll be doing hypothesis testing in the simplest possible cases. All right. So this is just really an introduction to what hypothesis testing is. All right. So let's get started. And this particular slide here just tells you why we might want to do hypothesis testing. We may have a research question that we want to answer. For example, it says here the second one, it says the National Association of Colleges and Employers stated that the average starting salary for students graduating with a bachelor's degree in 2010 is $48,351. And you wanted to know, is this true for your particular college? So that's a research question. That's something you would have to gather some data and then test to see if that hypothesis of 48,351 seems to be reasonable for your particular college. All right, so these are the types of questions that we can ask. We're going to use sample data to answer them. And today, again, we're going to strictly look at the theory behind hypothesis testing, so you have an idea of what it is and why we do it. And then we'll be doing the 2 types of hypothesis tests on Wednesday and also next Monday. Okay. Now in chapter 9, it says here we use the sample data to estimate the value of an unknown population characteristic. That is, we used a confidence interval to estimate a population parameter like a population proportion or a population mean. In this chapter, we're going to be using sample data to test a claim or hypothesis about the population characteristic. So a confidence interval, chapter 9, we estimated unknown population parameter by using a confidence interval. Here, we're actually going to be testing a claim. Somebody's going to make a claim, assign a value to the population parameter. We're going to see if it makes sense or not. So that's what the whole point of doing a hypothesis test is. And there's a particular procedure that we're going to go through in coming to a conclusion. All right. So what is a test of hypotheses? Test of hypotheses is a method, and you'll be learning what this method is, that uses sample data to decide between 2 competing claims or hypotheses about the population characteristic. All right, the first thing is the random value of the sample statistic that we get, like the sample mean or sample proportion. Does it seem to be a random occurrence due to natural variation? In other words, we make a claim about the population characteristic, and then we get the sample result. Does it seem reasonable that there could be a natural random occurrence with the population characteristic being what it is? Or is the value that we got from the sample so different from the assumed value for the population that we come to the conclusion that assumed value for the population is incorrect? It has to be something else. Okay. So it'll be clear in a minute what I mean by that. So the two competing hypotheses, one of them is called the null hypothesis, and it's denoted by an H with a little 0 as a subscript. Usually call that H naught or H sub 0. And it's a claim about a population characteristic that initially is assumed to be true. The competing claim, the one that we're going to test to see if it makes sense or not, is called the alternative hypothesis. It's denoted by the symbol H sub A, right? Well, it's HA, or the alternative hypothesis, and that is the competing claim, right? And what you're usually trying to do is determine if this claim is believable or not, the competing claim, right? So how do we come up with these hypotheses? We have to look at the research objective. In other words, we'll be looking at word problems and determining from the context of the word problem what the null and alternative hypotheses are. Now, the hypothesis tests are always about the population, never about the sample. All right. In other words, we are making a claim about a population parameter, such as the population mean or population proportion. We're not making any claim about the sample itself. The sample is just being used to test the claims, to test the hypothesis. All right. Now, an example or an analogy to what hypothesis testing is a criminal trial in a court. So I don't know if any of you have ever been on a jury duty, but if you were assigned, there's two types of cases. There's criminal cases and civil cases. With a criminal case, if it was for murder or for some other criminal matter, the assumption made before the jury looks at any of the evidence is that the person on trial is assumed to be innocent. So that's what we call the null hypothesis in this case. All right, the defendant is innocent. Notice that we're writing the words out. When we actually do hypothesis tests, we're going to be using symbols and numbers and things like that. But this is just an analogy. So what is the competing hypothesis? Well, it's that the defendant is guilty. Right? And in a court of law, how do you determine if the defendant is guilty? Well, there is so much evidence that to show that the defendant is guilty that it goes beyond a reasonable doubt. That's the term that they like to use in law. It goes beyond a reasonable doubt, all right, that the defendant is guilty. So enough evidence is gathered to say that, well, the defendant, it doesn't look like the defendant is innocent, the defendant is guilty. All right. And so to determine if the hypothesis is correct, the jury will listen to the evidence. Only if there's evidence beyond a reasonable doubt would the null hypothesis be rejected in favor of the alternative hypothesis. Now, here's a key point. If there's not convincing evidence, in other words, the evidence falls short of the criteria that the evidence should be beyond a reasonable doubt, then we would fail to reject the null hypothesis, right? We don't assume that the person is innocent. We just say there's not enough evidence to convict the person. So we fail to reject the null hypothesis. We don't accept the null hypothesis. We fail to reject it. That's how we say it, right? So that's the two decisions that we can make with hypothesis testing. Either there is enough evidence or compelling evidence to reject the null hypothesis and assume that the alternative hypothesis is true, or there's just not enough evidence to reject the null hypothesis, and we just state we fail to reject the null hypothesis. We never say we accept the null hypothesis. Right? So here are our two decisions. And this is the two decisions that we'll be making in hypothesis tests. And there's a certain procedure that you go through to come to one of these conclusions. It's not sort of a random thing. It's not something that you as an individual student will come up with your own conclusions. It is something that if you follow the procedure, anyone in the class will come to this exact same conclusion. So that's why we use this testing procedure. There's no doubts about it. All right. Now, how do we write in a statistical study, how do we write the null and alternative hypotheses? Well, what we do is we have H sub naught for or H naught, H sub 0 for our null hypothesis. So we need to write that. We need to write this here and put a colon. And then we're going to put a population characteristic. In other words, we'll put mu here if it's a population mean. We'll put P here if it's a population proportion. And that's, for this course, those are the only two options for the null hypothesis population characteristic. Either you're going to have a mu for a population mean or a P for a population proportion. All right, that's it. So it's not much, you don't have a whole lot of choices here to make. It's just one of those two. You're always going to put an equal sign for the null hypothesis. This is what the book recommends that you do. So you put an equal sign here, and then you're going to have to put a number here. So some number that represents a value for the population characteristic. Again, we'll see some examples in a second. So the null hypothesis always includes the equal sign. The hypothesized value is a specified number determined by the context of the problem. So the problem itself will tell you what that number is. You need to put in for the hypothesized value. The alternative hypothesis could be one of three cases, right? One of the cases is that we write it as HA, alternative hypothesis, colon. Then we have to put them, if this is a mu up here, we have to put a mu here. This is a P up here, we put a P here. So it has to be one of those two cases, a population mean or a population proportion. One of the three cases are greater than, in other words, the mu, for example, could be greater than 5 or some number. There's a greater than symbol here. Or an alternative hypothesis is that the population characteristic, like mu or p, is less than some number. Or the population characteristic is not equal to some number. So for the alternative hypothesis, the context of the problem that you read will tell you it's one of these three. It's either greater than, less than, or not equal to. So once again, the null hypothesis always has an equal to sign, and the alternative hypothesis will be one of these three cases, either a greater than, less than, or not equal to. And by the way, this hypothesized value that's mentioned here has to be the same number that's mentioned in one of these three cases. It has to match. So the population characteristic, the mu or p, has to match, and the number here has to match also. Okay. So there's certain terminology you have to know, and we'll see the reason for this next time when we actually do hypothesis tests. But there's these three types of alternative hypothesis. The first two, greater than and less than, are called one-tail tests because you're only interested in one direction. In other words, greater than. If you drew a normal curve, this would be what would be called a right-tail test. Again, you'll see that next time. Less than, notice pointing to the left. It's called a left-tail test. And not equal to, it's called a two-tail test. You're interested in both directions. Okay, again, this may be not clear to you at the moment. Don't worry about it. If you read chapter 10, it'll become clear also. But also my videos will help explain it better. All right, so let's practice writing these hypothesis statements, the null and alternative hypotheses. You always write two, the null and the alternative hypothesis, when you write your hypotheses. So here's a particular problem. It says sharing prescription drugs with others can be dangerous. A survey of a representative sample of 592 US teens, ages 12 to 17, reported This study reported that 118 of the 592 of those surveyed admitted to having shared a prescription drug with a friend. Is this sufficient evidence that more than 10% of teens have shared prescription medications with friends? All right. Well, this is a proportion problem. You could tell because it's a survey and you're counting the number of people who are admitting that they share a prescription drug with a friend. 118 people out of 592. And by the way, if you divide those two numbers, 118 divided by 592, you get your sample proportion, right? And what's the sample size? 592 teenagers. Now, is this sufficient evidence that more than 10% of teens have shared prescription medication with friends? So here is a claim that's being made. The claim is more than 10%, more than 10%. So we know that their population characteristic will be a population proportion, and the number that we're going to be using is 0.10 for 10%. Okay. So the true proportion, so the population characteristic is the true proportion P of teens who have shared prescription medication with friends. That's for all U.S. teens, not from the sample, but for everybody, all the teens ages 12 to 17. What's the hypothesized value? All right. What words indicate the direction of the alternative hypothesis? More than, see that? So the null hypothesis is always an equal to. We write it H sub 0. We always put that colon there. And then we put our population parameter here. In this case, it's a proportion problem. So we use P. We always use equal to. And again, the problem is telling us 10%, 0.10 or 0.1 is our null hypothesis. The alternative hypothesis is determined by this word more than. HA, the alternative hypothesis, colon, P is greater than 0.1. And that's what we're going to test. All right. We're going to see if there's enough evidence from the sample data to reject that the proportion is 0.1 and to state that the proportion is greater than 0.1. We want to see if there's enough evidence from the sample data. And again, I'll show you how to do that next time on Wednesday. All right, so let's just do some more examples. Compact fluorescent light bulbs are much more energy efficient than regular incandescent light bulbs. EcoBulb brand 60-watt CFL light bulbs state on the package, average life 8,000 hours. People who purchase this brand would be unhappy if the bulbs lasted less than 8,000 hours. All right, a sample of these bulbs will be selected and tested. State the hypothesis. Well, in this case here, the population characteristic is the average life. It's the mean life, right? Mean. It's the mean number of hours of these light bulbs. So we're going to be using mu here, not P, mu. Because we're measuring, we're counting, we're determining the number of hours, and that's we're measuring that. That's mu. All right, so mu is going to be there. The number that we're going to use is 8,000. And what is the alternative hypothesis? What's going to be the test here? Less than 8,000. We want to see if the bulbs last less than 8,000 hours. Okay. It says people would be unhappy if they lasted less than the 8,000 hours that are claimed by EcoBulb. So population characteristic is mu, true mean life of CFL light bulbs. The hypothesized value is 8,000. And less than is going to be our, as it says here, the direction, less than. So here's our null and alternative hypothesis. We're going to use mu in this case for both of them. We're going to use 8,000 for both of them. Always equal to in the null, less than in this case, in the alternative because it says less than in the problem. Pretty easy, right? You just read the problem and pick out the words. All right, here's another case here. Because in variation of the manufacturing process, tennis balls produced by a particular machine do not have the same diameters. Suppose the machine was initially calibrated to achieve the specification of mu is equal to 3 inches. All right, this is again, population characteristic is going to be the mean, mu. However, the manager is now concerned that the diameters no longer conform to the specification. If the mean diameter is not 3 inches, production will have to be halted. All right. So again, population characteristic is mu, population value is 3. And then in the alternative hypothesis, it says is not 3. Because if it's not 3, production will have to be halted. So in this particular case, it's a bad thing if it's less than 3 or greater than 3. All right. Both cases are considered to be bad, so we have to state it as a not equal case. All right, not equal. All right, so the null again, mu is equal to 3. Again, we write it exactly like this. Now, some students and tests and so forth leave out the mu. I don't know why, but since you guys are going to be taking your tests as multiple choice, there's not going to be that problem. So anyway, just know that its mu is equal to 3, not p is equal to 3. The alternative, because it says not 3 inches, the mu is going to be not equal to 3. That is the alternative. All right. So in these cases here, we want to see if these particular pairs of hypotheses are written correctly, and if not, what's the error? Let's look at the part A here. It says the null hypothesis is mu is equal to 15. The alternative says mu is greater than or equal to 15. Oops, that's a problem. The alternative hypothesis, there's only 3 possibilities: greater than, less than, or not equal to. Notice it says greater than or equal to. Well, that's a problem because this says equal to also. This can never say equal to here. So that is not valid. Must only be greater than. Here's another situation. X bar is equal to 4. For the null, HA is X bar is less than 15. Now, this is no good either. It's actually 2 errors here. 2 errors. First error is that the numbers don't match. These numbers always have to match, the null and alternative. But also, the other thing is, on a hypothesis test, we never test the sample characteristic, the sample mean or sample proportion, and this is the sample mean. No, we're testing mu. We're not testing X bar. So this should say mu here. So the 2 errors are, these 2 should say mu, and these 2 numbers here have to match those 2 errors. All right. Let's look at this one. Well, p is equal to 0.1 for the null. P is not equal to 0.1. Alternative, notice that you use the population characteristic, p. Equal here, not equal here are valid. And 0.1 and 0.1 match. So this is a valid pair of hypothesis tests. There's the smiley face. Finally, we have this case, the null and alternative hypotheses. Null, mu is equal to 2.3. That's fine. The alternative is mu is greater than 3.2. Well, the greater than is okay, but here's the problem. The 3.2 and the 2.3 do not match. They have to match the valid hypothesis. Same number in both cases. Finally, H naught, P is not equal to 0.5. Oh, there's a problem right there. It always is equal to here. And then the alternative says P is equal to, oh, it can never be equal to here. So this is all a mess. All right. So that's the problem. All right. So hopefully you have an idea now how to write a null and alternative hypothesis in the correct way. All right. So when you perform a hypothesis test, you're going to make a decision. You're either going to reject the null hypothesis or you're going to fail to reject. So there's going to be enough statistical evidence from the sample to reject it, or there's not enough evidence from statistical evidence from the sample, and you're going to fail to reject it. Again, I'll show you the exact procedures of doing this next time, and also on Monday, next Monday. So when you make one of these decisions, there's a possibility that you could be wrong, right? Why? Because you're using a sample. The sample is not the entire population. So you run some statistical procedure. You come to a conclusion of one of these two. You either reject the null or fail to reject the null. But it's possible you made a mistake. Okay? You made an error. And that's always possible when you have a sample instead of the entire population. So since it could be, you could make a wrong decision for in each of these cases, or failing to reject the null, or excuse me, for rejecting the null, you could have made a mistake there, or failing to reject the null, you could have made a mistake there. Let me just give you the example with the courtroom. What if you reject the null? What if you find that the person is guilty and the person's actually innocent? That's okay. Well, there's been cases like that, right? People were put into prison and they didn't commit the crime. Or you fail to reject H0, okay? When actually H0 is false. In this case, that would be that the error would be in the courtroom case would be that you don't find enough evidence to convict the person, and the person actually committed the crime. So the person is freed when they should be in jail. All right. So those are the two types of errors. So the two types of errors are called type 1 and type 2 errors. So let me tell you what the type 1 error is. Suppose you come to a decision using your statistical testing procedure that you'll be learning, and you've decided there's enough evidence to reject the null hypothesis. Well, what if the null hypothesis is actually true and you're rejecting it? Then that is called a type 1 error. Now, the probability of making this type of error, since you don't know if the null hypothesis is true or not, in reality, you don't know. Otherwise, why bother doing the test? So therefore, since you don't know if H0 is true, you can actually calculate the probability of this type 1 error, the probability of it. And that is denoted by the Greek letter alpha. Okay. Alpha is used as the probability of the type 1 error. And this alpha, this probability of a type 1 error, is also called the significance level of the test. Now, don't confuse this term significance level with what we use for confidence intervals. Remember, we used the term confidence level. All right, that meant something completely different than this. In this context, significance level means the probability of a type 1 error, or alpha. Type 2 error is the error of failing to reject a null. Right? Not enough evidence to reject the null, when the null hypothesis is actually false and the alternative should have been chosen. The probability of a type 2 error is denoted by the Greek letter beta. All right. Now, by the way, we're not going to spend a whole lot of time on beta. We're going to show you in a couple of minutes to show you the relationship between alpha, the probability of a type 1 error, and beta, the probability of a type 2 error. There is a relationship there, but we're going to be focusing more on the alpha and less on the beta. All right. Now, in your book, and pretty much any statistical textbook that is an introduction to statistics, they talk about hypothesis tests. They create this grid. Along the top here is these cases where the null hypothesis is true in real life. Now, we don't know that. I have to tell you, in reality, we don't know if the null hypothesis is true or whether it's false. But suppose we assume in reality it is true, or suppose we assume in reality it's false. That's what these two cases are. What is reality in real life? What is the population? Is the population H0 really true, or is the population H0 really false? Well, we don't know it, but we're going to state it anyway. These two rows here, reject H0 and fail to reject H0, represents the statistical procedure that we're going to use using the sample data to come to one of these two conclusions. Either we reject H0 or we fail to reject H0. All right. So The question is, what do we put in these boxes here? What words do we put? Well, we're either going to put the word correct decision or correct, meaning we made the correct decision when we came to our conclusion with the statistical test, or we made an error. All right. So, for example, suppose H naught is true and we fail to reject it. Right. So suppose H naught is in reality true and we didn't find enough evidence to reject it. Well, that's a correct decision, right? So H naught is true, we fail to reject it. In this box here, intersects those two statements, and that's correct decision. Makes sense, right? If we didn't reject the null hypothesis and the null hypothesis is true, we didn't make any mistake. Now, we don't know that ahead of time, but if this is true, then we didn't make any mistake. All right. However, if in reality the null hypothesis is true, but we had enough evidence to reject it, that's our type 1 error. Okay. Now, suppose H naught is false in reality. Okay. And suppose the statistical test, we reject the null hypothesis. Well, we didn't make any mistake in this case, right? We rejected it, and it's actually false. So that's a good thing. We made a correct decision. And finally, if H naught is false and we fail to reject the null hypothesis, then we made that type 2 error. All right, so this is our little box here that helps us determine whether we made a type 1 or type 2 error. All right. So let's take a look at an example and a couple of examples about type 1 and type 2 errors to see if we can determine what they are based on the problem. All right, the U.S. Bureau of Transportation Statistics reports that for 2009, 72% of all domestic passenger flights arrived on time, meaning within 15 minutes of its scheduled arrival time. So that's what they mean by arrived on time, plus or minus 15 minutes, the actual scheduled time of arrival. Suppose that an airline with a poor on-time record decides to offer its employees a bonus if, in an upcoming month, the airline's proportion of online flights exceeds the overall 2009 industry rate of 0.72. In other words, just for that one particular month, a sample obviously is being done, and for that month. And if in that particular month, if the airline's proportion of on-time flights exceeds 72%, all the employees get a bonus. All right, so null and alternative hypotheses, pretty obvious that this is a proportion problem. Taking a percentage of all the flights, we're counting the number of flights, right, that are on time and dividing it by all the flights, right, all the domestic flights. And that's how they came up with the 0.72. So P is the appropriate population characteristic. The null hypothesis is equal to 0.72. And then the employees will get a bonus if the proportion exceeds, proportion of on-time flights exceeds 0.72. That makes sense, right? Apparently, they're doing a better job if this percentage or this proportion goes up. So P is greater than 0.72 is the alternative. Now, why don't we state the type 1 error in this case here? Well, the type 1 error, once again, is we reject the null hypothesis in favor of the alternative hypothesis when the null hypothesis is true. So suppose the sample data for that month indicates strong enough evidence to say that proportion is really greater than 0.72. So what happens? The people get a bonus, don't they? Well, the type 1 error would say, in reality, they didn't do over 0.72. They did 0.72 or even less than that. So a type 1 error in this case, they got their bonus when they didn't deserve the bonus. So the airline decides to reward the employees when the proportion of on-time flights doesn't exceed 0.72 in reality. All right. So they're getting rewarded when they didn't deserve to be rewarded. That's a type 2 error. Type 2 error says we don't reject the null when the null is actually false. So that the statistical evidence from the sample of data says there's not enough evidence to conclude that their on-time flights exceed 0.72. But in reality, they did exceed 0.72. So what ended up happening? The result of this type 2 error is that the employees did not get their bonus when they should have gotten the bonus. The airline employees did not receive the bonus when they deserved it. All right, let's do another example. In 2004, Vertex Pharmaceuticals, a biotechnology company, issued a press release announcing that it had filed an application with the FDA to begin clinical trials on an experimental drug, a VX-680, that had been found to reduce the growth rate of pancreatic and colon cancer tumors in animal studies. Data resulting from the planned clinical trials can be used to test the true mean growth of tumors for patients taking the experimental drug. So what is the null hypothesis? The mean growth rate of tumors for patients not taking the experimental drug, and the alternative is that mu is less than the mean growth rate of tumors for patients not taking experimental drug. In other words, the experimental drug actually lowers the mean growth rate of tumors, right? That would be a good thing. So either the new experimental drug doesn't have any effect, which would be H0, or maybe even a worse effect, or it has a good effect, which would be the alternative hypothesis. So what is a type 1 error here? Type 1 error would be what? We reject the null, that is the mean growth rate for patients not taking the experimental drug it's actually went down. So there's enough evidence to show it went down when in reality it didn't go down. So in other words, the evidence shows the drug worked when it in reality did not work. That would be the type 1 error. Obviously, if it worked and it didn't really, I mean, if the evidence shows that it worked when it really didn't work, okay, then what would happen? Well, the drug would be shown to be effective, right? When it really isn't effective. Okay. So the company would devote resources to an ineffective drug. Type 2 error. Well, that's when we do not have enough evidence to reject the null when the null is actually false. So we don't have enough evidence to reject the null when the null is actually false. So the evidence from the statistical study may show that the drug is ineffective when it really is effective. Okay. And what's the consequence? That no money is devoted to further research for an effective drug. So they may abandon this drug when it's actually effective, and that would be a bad thing. All right. Now this slide here, it won't be tested on the final exam. I should let you know that because it's a more advanced idea. So I'll go through it, but just know this is just for your understanding the relationship between alpha and beta, the probability of type 1 error alpha and the probability of a type 2 error beta. But it's a pretty advanced concept, and it's not something I'm going to spend a whole lot of time, but I will mention it briefly. So it says here the ideal test procedure would result in both alpha being 0 and beta being 0, right? You don't want any errors at all. No type 1 errors, no type 2 errors. But in reality, this is impossible to happen because the probability of the type 1 error influences the probability of the type 2 error, and vice versa. They're actually related to each other. All right, so how does it work? So in reality, and you'll find that out next time, The alpha, if somebody's going to be doing some research, they're going to select an alpha ahead of time. A common alpha is 0.05 for the probability of a type 2 error. So you select this ahead of time, what you feel like is acceptable, type 1 error. But you don't have any control over the type 2 error, the beta. All right, so you select alpha, and beta is basically left to its own devices. Now, how did the two, how are they related to each other? Again, I'll show that in a second. So anyway, you select the significance level alpha, 0.05. Again, it could be 0.05, 0.01, some small value. It results in a test procedure that, used over and over with different samples, rejects a true H0 about 5 times in 100. So what does that mean? That means if you ran this procedure over and over again, which you're not going to be doing, but if you did, that if you selected alpha is equal to 0.05, then in about 5% of those times that you ran this procedure, you would end up with a type 1 error, right? You would end up rejecting the null, and when the null shouldn't have been rejected. Now, most researchers want to reject the null hypothesis because they believe the null hypothesis is false, all right? So they want to do that. But when you select your alpha, you have to select something. Because if you're dealing with a sample as opposed to the population, there's always a chance for an error. You want the probability of a type 1 error to be small. Okay. But here's the problem. If you choose alpha to be too small, the probability of a type 2 error actually goes up. All right? And that is an issue. So it says here, suppose you have these two hypotheses. The null is p is 0.5. The alternative is p is greater than 0.5. Now, as you'll find out next time, we're going to be using a bell-shaped curve to work with this, the normal curve. And the question is, where do we do something with this alpha on this curve here, this probability of type 1 error? And the answer is yes. All right, suppose you drew the 0.05, your alpha over here. This is 5, let's say it's 0.05, right? So this is the part of the curve that represents alpha or the type 1 error. Now, why is this a type 1 error? This 0.05, for example, alpha is 0.05. Well, because the mean is 0.5. We're assuming that the null hypothesis is true. And when we do hypothesis tests, just like in a court of law, we initially assume that the person on trial is innocent. So before we actually look at any of the evidence, we're going to draw a normal curve. We're going to put our p right in the middle. The value here, 0.5, is right in the middle. All right, that's our mean of the population, right? 0.5. So we're going to assume that's true. So that means this curve is centered around 0.5. And this 0.05 out here on the right tail, and why are we picking this tail out here? Because we're saying that p is greater than 0.5 for the alternative. Right? So if it's greater than 0.05, it's something greater out here. And we're saying there's a 5% chance that we might make an error, that will reject the null when the null is assumed to be true. That's called the type 1 error. Your alpha of 0.05 is on the right here. This was less than, and then we'd be dealing with the left tail here instead of the right tail. Now, if the null hypothesis is actually false in reality, okay, in other words, you reject the null and the null hypothesis is false, then p is greater than 0.5. It's some value bigger than 0.5. The center of the normal curve is actually out here somewhere. Okay, does that make sense? It means that the whole curve actually is shifting to the right here with a new p, the new mean, the new p being something bigger than 0.5, somewhere out here. Now this red here still represents what? The probability of a type 1 error if this was true, if this curve was true. But what if the null hypothesis is false? And this is the true curve for P, all right, with a mean of bigger than 0.5, somewhere out here. Then this area here would be the probability of a type 2 error. In other words, if we assume that the alternative, if we make the assumption that the null hypothesis is false, which would be this curve, the type 2 error would be, oh, it's that part of the curve where I would state that the null hypothesis is false, but the evidence is that it's actually true. The evidence states that it's true. That's the beta. That's the probability of a type 2 error. All right, it's the blue here. So the red represents the probability of a type 1 error. We're assuming that the middle of this curve is 0.5. We're assuming H naught is true. And then, so the red represents the probability of a type 1 error. However, if we assume H naught is false and the alternative hypothesis is true, suppose this is the curve, the correct curve, right, for P being greater than 0.5 in the middle, the probability that we made a type 2 error would be, assuming that the null hypothesis is false, it would be this curve here, and then our test says, no, it's not false, it's true. The null hypothesis is not rejected. So that would be this blue area here. This would be our probability of a type 2 error. A little bit of a complicated concept, but I hope you can get the idea. Now, here's the deal. Suppose we changed alpha to 0.01. So there's a smaller area, it's a smaller chance of a type 1 error here. But let's see what happens with the type 2 error. Well, again, type 2 error assumes that the population proportion is greater than 0.5, so it would be the second curve here. And now this area here is the probability of a type 2 error. Notice it's gotten bigger. So here's the takeaway from this. As alpha gets smaller, the probability of a type 1 error gets smaller, the probability of a type 2 error gets bigger. Right? Sometimes we don't want the type 2 error to be too big. So what do we do? Well, we have to balance the two, right? You don't want alpha to be too big, because we don't want the type 1 error to be too big, because we do want to reject the null hypothesis. That's our goal. And we don't want us to make an error doing that. So we want alpha to be small, but we can't afford for it to be too small, because then we would be making a bigger type 2 error. So we come up with a balance, and most people have determined that alpha is equal to 0.5 is a nice balance between the type 1 and type 2 errors. Okay. So this is our conclusion. After assessing the consequences of type 1 and type 2 errors, identify the largest alpha that is tolerable for the problem. So we don't want too big of a type 2 error, too big of a beta. All right. So again, in many cases, especially in the social sciences, they use 0.05 for your alpha for the probability of a type 1 error. All right. So again, that was just meant to show you that there is a relationship between the two. Again, I will not be testing you on beta itself. All right, beta itself. I won't be asking you to calculate. However, one thing I could test you on, if I so desired, was that the smaller the alpha, the bigger the beta. The bigger the alpha, the smaller the beta. I could certainly test you on that, but I will never test you on determining what beta is, that probability. You can calculate it, but it's a little more complicated. In my view, it's beyond the scope of this course. So I won't ask you specifically to calculate what beta is. All right, anyway. So let's look at this particular problem here. The EPA has adopted what is known as the lead and copper rule, which defines drinking water as unsafe if the concentration of lead is 15 parts per billion or greater, or if the concentration of copper is 1.3 parts per billion or greater. The manager of a community water system might use lead level measurements from a sample of water specimens to test the following hypotheses. So they're, in this particular case, you're looking strictly at the concentration of lead, which is the 15 parts per million. So they're saying it's unsafe if the concentration is 15 parts per billion or greater. All right. Now, the manager of a community water system might use lead level measurements from a sample of water specimens to test the following hypotheses. So in this case, they're giving the hypotheses because it's not clear what they're really testing. But in this case, the alternative hypothesis is saying what? It's saying the water's safe. Because in the problem, it's saying if it's 15 or greater, it's unsafe. So the alternative is it's safe, because that's the purpose of the community water system, is to make the water safe. So they're going to test to see if the water is safe, right? The null hypothesis, mu is equal to 15, is really the unsafe case. What's the type 1 error in this case here? The type 1 error is that we're going to reject the null, right? And we're going to say that the water is safe, when in reality the water is unsafe, right? So the water source meets EPA standards when the water is really unsafe. But the consequence, well, it's not a great consequence, isn't it? If we say the water is safe, we're not going to really do anything to make it better, and people are going to suffer as a result of it, right? Unsafe water is, may lead to some unhealthy consequences, some possible health risks to the community. Type 2 error would be there's not enough evidence to reject the null, all right? When in reality, the water's safe, all right? In reality, the alternative hypothesis is true. So in this particular case, we would probably say the water is unsafe when it's really safe. So the water source does not meet EPA standards when the water really does. But the consequence of that, community might lose a good water source, right? They might shut it down. Which one is the most serious of the two? Type 1 error is more serious because the community would lose a more, so most people would consider the type 1 error to be more serious, right? Yeah. Why? Because if we go back to it, it leads to the conclusion the water source is safe when it really is unsafe. So we're making the people, people will end up getting sick. Here, type 2 error says that the community might lose a good water source. Well, yeah, but does it lead to any sickness or disease? No. It was just a mistake and didn't lead to any health consequences for the community. So the type 1 error is the one that is worse, not the type 2 error. All right. So we've done enough today as an introduction to hypothesis testing. Hopefully you learned something from it. What we're going to do next time is we're going to do what's called the large sample hypothesis test for a population proportion. I'll show you all the steps that you have to go through to run this test and the different types of tests that we can run. We talked about the one-tail test and the two-tail test. We're going to go through all of that. So it's a little bit extensive, but again, we'll spend our time on that, and I'll show you, do some examples, from the textbook that will illustrate how to do these types of tests. And then next Monday we'll do the next section, which is the hypothesis test for a population mean, and I'll show you how to do those next Monday. One thing I would like to do now, so let's get out of the slides, is go to a couple problems in the textbook that illustrates what we went over today. So you go to page 509 of the textbook, and we'll go to 10.2 here. These are 5 different cases of potential hypothesis tests. We want to see if they were set up correctly. So this is another illustration of what was done in the book, in the slides that we looked at today. So let's look at the first one. It says the null hypothesis, the mean is 15. The alternative of the mean is 15. Well, the alternative hypothesis can never be 15. All right. So back to our notes here. The alternative can never have an equal sign. Okay, so that's the problem with that one. Second one says P is the null hypothesis, P is equal to 0.4. The alternative is that P is greater than 0.6. Well, the P is okay, the greater than is okay, the equal to here is okay. What's not right is that these two numbers don't match. The two numbers have to match, and that's the problem with part B. The numbers for the two hypotheses have to match. C, it says mu is equal to 123 for the null. That seems right. The alternative is mu is less than 123. That seems right. Hey, C looks good. C is a valid hypothesis, set of hypotheses. All right, and if we go back, we'll see complies with the rules. Yeah. All right, D, mu is equal to 123 is the null. Mu is equal to 125 is the alternative. Well, there's two problems. Can't have an equal to sign in the alternative, and the numbers don't match. So there's two issues here with D. And finally, with E, it says p hat. The null says p hat is equal to 0.1. The alternative says p hat is not equal to 0.1. Well, the 0.1s match. The equal to is okay here. The not equal to is okay here. What's bad about this hypothesis is that you have p hat here. We never test samples statistics. In hypothesis, we test population parameters such as p and u. In this case, it should say p, not p hat here, and it should say p over here. So it's the cannot use sample statistic p hat. Hypotheses must use population parameter. All right, let's look at 10.7 on the same page. All right, let's go scroll down. Looks like it's the next page, 10.7. All right, here we go. I'll just read through it. It says a study sponsored by the American Savings Education Council included data from a survey of 1,752 people aged 19 to 36. One of the survey questions asked participants how satisfied they were with their current financial situation. Suppose you want to determine if the survey data provides convincing evidence that fewer than 10% of adults aged 19 to 39 are very satisfied with their current financial situation. Right? Fewer than 10%. So P is the proportion of adults aged 19 to 39 who are very satisfied with their financial situation. What hypotheses would you test? Well, certainly P is equal to 0.10 is the null hypothesis. Okay. And they say fewer than here, fewer than. That has to be the alternative hypothesis. So P is less than 0.1. So let's take a look at the results. There you go. The context of the problem states exactly how to write the hypothesis. You would write it this way. We don't use words, we use symbols when we do hypothesis tests. All right, let's go back and we'll do, which I think the next problem was what? Number 10. The same page. A cruise ship charges passengers $3 for a can of soda. Because of passenger complaints, the ship manager has decided to try out a plan with a lower price. He thinks that with the lower price, more cans will be sold, which would mean that the ship would still make a reasonable total profit. With the old pricing, the mean number of cans sold per passenger for a 10-day trip was 10.3 cans. It's the mean number of cans sold per passenger for the 10 days, 10.3 cans. Suppose mu represents the mean number of cans per passenger for the new pricing. What hypotheses should the ship manager test if he wants to determine if the mean number of cans sold is higher for the new pricing plan? That is the higher, right? So mu is going to be our population parameter that we're going to use, and 10.3 is going to be the number that we use for the null and alternative, and greater than is going to show up in the alternative. Let's go ahead and show you the answer. I hope you agree that the null should be mu is equal to 10.3, and the alternative should be mu is greater than 10.3, because that's what they're claiming. All right, so we'll now go to page 513 and go to number 12. So 513 and number 12. Okay, that's the first one here. It says researchers at the University of Washington and Harvard University analyzed records of breast cancer screening and diagnostic evaluations. Discussing the benefits and downsides of the screening process, the article states that although the rate of false positives is higher than previously thought, now let's just say what a false positive means. A false positive test would mean what? It would mean that the test shows that you have the cancer, and false meaning then in reality you don't have the cancer. All right, so a false positive means that the test shows you have cancer when in reality you don't have cancer. So although the rate of false positives is higher than previously thought, if radiologists were less aggressive in following up on suspicious tests, the rate of false positives will fall, but the rate of missed cancers would rise. Okay. Suppose that such a screening test is used to decide between a null hypothesis of no cancer is present and the alternative is cancer is present. Okay. A, what a false positive, thinking that cancer is present, when in fact it is not. So let's think about a false positive, right? We're thinking that the cancer is present. The test is showing the cancer is present when it really isn't. So we're thinking that the alternative hypothesis is true when in reality the null is true. What type of error is that? That's the type 1 error, right? When we are assuming that alternative is true when in reality null is true. Describe a type 1 error in the context of this problem and discuss the possible consequences of making a type 1 error. So let's so a type 1 error would be that a diagnostic test says that you have cancer when you really don't. But the consequence is that you would receive treatment for cancer when you did not need treatment. C, of course, asks for a type 2 error. That's what the next question is. Describe a type 2 error and what the consequences are. Type 2 error, now if we go back to the problem, type 2 error would be what? Would be assuming, would be concluding from our diagnostic test that the person doesn't have cancer when in reality they do have cancer. So let's go back to the problem. Type 2 error would be that a diagnostic test states that you do not have cancer when you actually do. The consequence is that you do not receive the treatment that you need, right? And by the way, this is called a false negative, right? Your test is saying that you don't have the cancer, and in reality, you do. That's obviously the type 2 error is much worse here, because you can end up dying, right? You can end up not receiving any treatment for cancer, and the cancer could grow from there and kill you. So that's called a false negative. All right, so this is examples of type 1 and type 2 errors in the context of a diagnostic test for disease. All right, so page 513, number 13. Back to the here. This one right here for MRIs. It says there's a paper about MRIs looking at breast cancer. So it describes a study of the use of an MRI exams. Let's go to the next page. And being used to diagnose breast cancer. All right, the purpose of the study was to determine if MRI exams do a better job than mammograms, determining if women who have recently been diagnosed with cancer in one breast have cancer in the other breast. The study participants were 969 women who have been diagnosed with cancer in one breast and for whom a mammogram did not detect cancer in the other breast. All right. These were 969 women who had been diagnosed with cancer in one breast and for whom a mammogram did not detect cancer in the other breast. So these women had an MRI exam of the other breast, and 121 of those exams indicated possible cancer. All right, so the mammogram didn't, but the MRI did. After undergoing biopsies, it was determined that 30 of the 121 did in fact have cancer in the other breast, and that means the rest of the 91 did not. Anyway, the women were all followed for 1 year, and 3 of the women for whom the MRI exam did not indicate cancer in the other breast were subsequently diagnosed with cancer that the MRI did not detect. All right. All right, suppose that for women recently diagnosed with cancer in one breast, the MRI is used to decide between 2 hypotheses. First hypothesis is that a woman has cancer in the other breast, and the alternative is that the woman does not have cancer in the other breast. All right. So one possible error would be deciding that a woman who does have cancer in the other breast, right, is cancer-free. All right. Is this a type 1 or type 2 error? All right. So it would be deciding that a woman who does have cancer in the other breast. Well, which one is that? All right. Well, that's H naught. All right. So we're saying H naught is really true. But we're also, the MRI is saying that the person's cancer-free. Okay. Which means this is true, right? So the diagnostic test is saying reject the null and say the person doesn't have cancer. Okay, hold on a minute. All right, here you go. So the test is saying, the MRI is saying, person's cancer-free, which is the alternative, when in fact the person does have cancer. So when we say the alternative hypothesis is true, when in reality H naught is true, then that is a type 1 error. So the answer to A for this problem here is type 1 error. Now, how do we find the probability of a type 1 error using the chart that we just came up with here? That's what they're going to be asking for. Right. How do we approximate the probability of this error? Well, we're assuming, well, remember on the top here is reality. Person either has cancer or does not have cancer in the other breast. All right. Here is the MRI testing. Either it shows positive for cancer or shows negative for cancer. Well, what they're saying here, the woman does have cancer. So cancer is present. So we're dealing just strictly with this column here. 33 men there's 33 women who have cancer. Out of those 33, 3 of them, the MRI was negative for cancer. In other words, showed that you did not have cancer. So the probability of a type 1 error in this case would be 3 divided by 33. 3 divided by 33, which is equal to 0.091. How about a type 2 error? Right. Now, what is a type 2 error? I think that's what they're asking next. Right. Type 2 error would be what? It would be not rejecting the null when the null is actually false. Okay. Then we don't reject the null. In other words, a person, there's not enough evidence to show that they don't have cancer. So the woman in reality does not have cancer. It would be this column here. But the MRI is positive for cancer. That would be the type 2 error. So it would be the total number of women who don't have cancer in the study was 936. The total women where there was a type 2 error would be 91. 91 divided by 936 is the estimate of the probability of a type 2 error. And the answer is 0.097. Okay. Now the rest of this here on this sheet we're going to be covering next time. So I'm not going to post this yet, this problem sheet yet. I'll start posting that next time, or maybe even on Monday, next Monday. All right. So anyway, that is it for today. And hopefully that was somewhat clear to you. Again, you have the opportunity to view this video more than once. You can rewind and see exactly, hear things over and over again. Anyway, we'll do real hypothesis testing next time, show you all the steps of it. Again, on Wednesday, we'll talk about hypothesis testing for a population proportion, and I'll show you the same procedures on next Monday for population means. All right, so that's it for now, and have a very good day. See you soon.